Hello, Mile High Video. Are you ready for the most exciting spec development updates of the whole show? This might not be that, but we will tell you everything that's going on with media source, EME, and media capabilities. So thank you very much for your attention.
Thank you, Joey, for raising everybody's expectations. I'll try to exceed them. Hello, everyone. This is Matt Wolenetz with some updates on media source extensions, also known as MSE. MSE has been evolving since it became a REC standard in late 2016, and we are now working on features to be included in the MSE version 2 specification. So after reaching REC and prior to the formation of the current media workgroup, incubation of several new MSE features began. These and other features will be coming soon to the MSE editor's draft spec. I will talk briefly about a few of these features, and I'll conclude with a slide with links to more details and demonstrations. First, multiple browsers, including Chrome, Firefox, and Safari, have shipped a new seamless codec switching API known more familiarly as source buffer change type. Another highly anticipated MSE feature that has recently landed in an experimental implementation in Chrome is the ability to use the MSE API from a worker context, aka MSE and workers. For both change type and MSE and workers, I'll go into more detail in a moment. But first, beyond those, I've listed here several other features which are either currently being prototyped or are on deck, if you will, for potentially being added to MSE. One exciting new feature being prototyped right now is the ability to buffer web codecs media for playback with MSE. One use for this is more efficient transmuxing. The feature would let web applications avoid having to mux or remux their media for use with MSE. For example, playback of HLS content using MSE frequently requires web applications to transmux MPEG transport streams to fragmented MP4. With this feature, the web app could just demux the transport stream, populate web codecs encoded audio and video configs and chunks, and then feed those directly to new MSE methods without having to first put them back into a container format like MP4 or WebM. We're also considering enabling buffering of already decoded web codecs audio and video frames for playback with MSE, though it is uncertain if the use case for this is as strong, considering the buffering overheads may make a streaming API like WebRTC or direct use in web codecs a better fit for playing already decoded content. One possibly strong use case could be direct support for decoded PCM audio in MSE buffering and playback, letting apps directly buffer PCM content for playback with MSE. Another feature that is on deck for potential inclusion in MSE v2 is giving apps the ability to specify more precisely how MSE makes room for newly appended media. This feature is known more familiarly as eviction policies. It could allow for new eviction models, perhaps even letting the application agree to let the browser preemptively evict media. For instance, this could remove the only known technical blocker of which I'm aware to iOS supporting MSE, or to buffer media with very rare keyframes via another policy, which could enable more performant live low latency scenarios. And we'd like to solve the interoperability problems that occur when different MSE implementations produce different buffered range results for the same supported media. Several features revolve around this theme, including getting more metadata about currently buffered media, and especially an API for letting the web app determine more precisely when a buffered range gap could occur and what the player behavior should be at such gaps. Note that these are just a subset of about 19 features varying sizes currently under consideration for inclusion in MSE v2. Web standards thrive when there is collaboration and feedback. MSE so far has benefited greatly from wide use, and we'd love to have your input on MSE features that you want in v2. Next, I'll give more details for the new source buffer change type API. Here is an example of how to use the source buffer change type API. Suppose you want to buffer two different kinds of video in the same source buffer, such that if there is no buffered range gap between them, they play seamlessly from one to the other. Change type lets you tell MSE that upcoming appended media will be for a potentially new byte stream format or codec. Like the existing constraints on MSE appends, change type has similar. It requires that an initialization segment be appended next before a media segment of the new type, and that the initialization segment satisfies the usual constraints, that it has the same number of each type of track, be they audio or video, and those constraints apply across all init segments for that same source buffer, even if there are intervening change type calls. And if there are more than one audio or more than one video track in the source buffer, then the track IDs must also match, even if the byte stream format changes. Change type lets MSE apps play different media and codecs within the same media element without having to use different media source objects or switch tracks. Both of those workarounds for previous lack of this API are not ideal. They impaired the UX by adding latency at points where the media switches. Change type lets the media play seamlessly across such points in the presentation timeline. Next, I'll give more details for the new MSE and Workers API. Here is an example of how to use the new MSE and Workers API. Suppose your web app is using the main window context heavily for other work. It can become so busy that opportunities to fetch and append media to a media source are infrequent and risk underflowing the playback of the media. In other words, you could get buffering jank when trying to use traditional MSE on a heavily contended main thread. So, what to do? You could refactor the app and maybe do less work on the main thread, or you could move all of your usage of the MSE API into a dedicated worker. The latter approach is the gist of MSE and Workers. It exposes the same MSE API you're used to being used from a dedicated worker context. So how does this work in action? First, you can check and see if the implementation supports MSE and Workers, and you don't need to start a worker thread first to figure that out. If the static can construct in dedicated worker attribute exists on the media source and is true, then you can be assured that the MSE and Workers API is available. So once you know you can use MSE in a worker, you may wonder, how do I extend the main thread media element with MSE if MSE is in a different execution context like this? The answer is hopefully both simple and unsurprising. Have your worker script create an object URL for the media source and post message that object URL over to your main thread script. In the main thread, use the object URL as the source attribute on the media element, and voila, the two will be attached. With an experimental version of this in recent Chrome, Canary, and Dev releases, I recommend you try it out. We're very interested in any feedback you may have for MSE and Workers, as we are working to standardize it. Next, I'll give some links where you can find more details about all these features, including a link to a demo for MSE and Workers. As promised, here are links to all the features I've mentioned, including that MSE and Workers demo. If you have any feedback, please comment on either the spec issue for the feature or create a new one in the MSE spec issue tracker. You could also reach out directly to the MSE spec editors, including myself, or if it's an implementation issue, file a bug on the implementation. All are great ways to help make MSE v2 excellent for web developers. I thank you for your attention, and I'll pass the baton over to Joey to talk about EME next.
Hi everyone, this is Joey Parrish with some updates on encrypted media extensions. The latest draft of EME adds just a few things so far. Encryption scheme queries, the persistent usage record session type, aka secure stop, and a key status called usable in future. I'll go into more detail on these in a moment. Beyond that, there are proposals for HTTP status detection, which I'll demonstrate as well, and a way for CDMs to communicate with applications about surprise session closures. We don't yet have a solid proposal related to key rotation, though there are several open issues related to that in scope for this revision to the spec. Persistent usage record is a new session type compared to the rec spec, though it was in an earlier draft before that. It persists records of first and last decryption times, but not the keys themselves. This allows a service to get a record of license usage when the license is removed. Usable in future is a key status that is in many ways the polar opposite of expired. You can't use the keys yet, but they will be considered valid at some point in the future. This is equivalent to a feature Android Q added in its DRM APIs already. HDCP status queries allow an application to find out what effect a certain HDCP policy requirement in a license would have right now. Apps can use this information to make content decisions if they choose, as an optimization. Here we have an example of the HDCP status API in action. You can ask what key status you would get for a certain HDCP version, which is HDCP 1.0 here. If the CDM wouldn't be able to play with such a license policy, you can find out now, even before you've done the license exchange. Common encryption, as we all know, is a statement only half true. Broadly, there are two mutually incompatible schemes in use today: CTR mode, aka CE and C, and CBC mode, aka CBCS, where the last S stands for skip. Today, you probably have to guess which ones are supported by a browser, based on the user agent string, or the CDM in use, or something similar. With encryption scheme queries, you can stop guessing and just ask. The spec currently includes three enum values: CE and C, CBCS, which implies any skip pattern must be supported, and CBCS-1-9, which only means the common 1 to 9 pattern supported by all the older iOS devices. Now, new APIs are great, but unfortunately, you're only going to get them when devices get updates. And you know your devices do not get updates. So to make life easier, we also shipped an open source polyfill for this. Instead of guessing on those browsers and devices that don't have the API yet, you can let the polyfill guess for you. It does this based on very conservative assumptions for each key system that hold for all devices where those key systems have ever shipped, so it's extremely safe. This polyfill not only adds encryption scheme queries to EME, but also media capabilities. Here is an example of what those encryption scheme queries look like. You just add encryption scheme to each capabilities object, and EME will choose a working configuration for you. Since these encryption schemes are mutually incompatible, you can then use the information about what scheme was chosen to load a content URL that was encrypted in the supported scheme. Now I will hand it over to Chris to talk about media capabilities.
Hi, I'm Chris Cunningham. I am here to talk about some new features in the media capabilities specification, as well as some related additions to CSS media queries. On this slide, I'll run through a list of new features since last Mile High, and then go more in depth on the next two slides. The first new feature is the ability to query for EME decoding capabilities. This feature launched in Chromium last year. We also specified how to query for HDR video formats, and then related to that, we worked with CSS to add a new dynamic range feature to the media queries level 5 spec to query for when your display is HDR capable. Finally, there is some ongoing work in that specification to add video prefix properties to media queries to surface when devices like TVs are capable of rendering video in their native resolution, like 4K, while having a much more limited capability for graphics. On this slide, we're calling media capabilities with an EME configuration. The first three fields in the dictionary are the typical inputs for audio and video, and then the key system configuration specifies that this stream requires the Widevine key system with a particular robustness level. If you want to use media capabilities for EME, it's critical that you supply these details. EME content will use different decoders from clear content, and that results in different answers for questions like codec support and playback smoothness. The call returns a promise, which resolves to describe the requested capability. This includes whether it's supported at all, whether it's predicted to be smooth, and power efficient. For EME queries, it will also include a key system access object whenever the configuration is supported. The idea being that you can call media capabilities instead of request media key system access, and then use the return to info to set up your EME playback just as you do today. Here we're making a call to media capabilities with an HDR configuration. Prior to call, we first check with window.matchMedia for the dynamic range CSS media query to determine whether the screen supports HDR. Finding that it does support HDR, we call media capabilities with the typical video dictionary and then 3 additional inputs highlighted by that red box for the HDR aspects of this stream. As with EME, the return from this query will tell you whether the configuration is supported, smooth, and power efficient. And just a reminder, this work is still in progress in Chrome.
Thank you everybody for your time. Assuming that all of our home internet connections are working, we will now take some live questions.